Hello and welcome back to Ordinary Differential Equations, the video series where we learn how to tackle problems with differential equations. And in fact, in today's part 30, we will learn about the method of integrating factors, which is actually equivalent to the method known as the variation of constants. So these are a lot of names, but the essential part is that these methods give us the solutions of linear ODEs. More precisely, they give us a general formula for the solution set of a system of linear ODEs. But now, before I show you this nice result, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, with a membership on Steady or Patreon, you can use the link in the description to download a lot of additional material. And with that out of the way, I would say we can immediately start with the general assumption of this video. It is the same as in the former videos, we have a system of ODEs which are linear. And just to make it clear, this also means that the two maps that are involved here, the matrix mapping and the vector mapping, are continuous maps that are defined on an interval of R. And under these assumptions, I want to show you the method of integrating factors, and let's start with the simplest case. This is the one-dimensional case, and we actually already have discussed that in part 7. This also means that there is no matrix involved, it's just a real-valued function, so let's use a lowercase a to denote that. So the idea here is that we use the knowledge of the one-dimensional case to generalize it to the n-dimensional case. And there, first of all, if we just consider the homogeneous part, then we already know the general solution, because this one is given by the exponential function. Indeed, the only thing we have to do in the exponent there is to put a primitive and antiderivative of a in. So for example, we can just say integrate from t0 to t. Now obviously this is a special solution that solves the initial value problem for the homogeneous part, where at t0 we want to get out 1. So let's call this solution p of t, and then we know that p of t0 is equal to 1. And obviously if we have a different initial value at t0, we can just scale this solution. Okay, and now we want to go back to our original linear ODE as an initial value problem. So in general we can just say x of t0 should be equal to x0. And now in order to do that, we can just recall part 7 with the method of integrating factors. So if you don't remember that, I can quickly show you, and first we bring the homogeneous part to the left hand side. And then we have to multiply on both sides with an integrating factor, which is the exponential function, where an antiderivative of this function, including the sign, is in the exponent. Hence this one here is the function we have to multiply, and now because of the exponential function involved, we see that this is actually just the reciprocal of p of t. So in short, we just have an inverse of a real number here. And therefore, to keep it short, I will just write p of t to the power minus 1. And now by the power of the product rule, this integrating factor just works on the left hand side. So instead of a sum, we just have d dt of a product, namely p of t inverse times x. And on the right hand side, we don't do anything because we just have p of t inverse times p of t. And now you see it's called an integrating factor because now we can solve the OND just with an integration. And to keep it simple, we just integrate on both sides from t0 to t. And this implies that here on the left hand side we have the solution x of t minus the lower limit x of t0. And moreover, there we can actually use that p of t0 is equal to 1. And indeed on the right hand side here we cannot do much because there we just have to calculate a whole integral. Therefore in the general formula this remains as p of s to the power minus 1 times b of s. And with that we are almost done, because as you can see in the last step, we just have to bring everything to the right hand side. This means we just have the initial value x0 plus the whole integral times p of t. So you should not forget that we actually have parentheses here. And that's it. This is the unique solution for our initial value problem. Hence, the whole thing comes down to first solving the homogeneous part and then calculating this integral. But from the mathematical point of view, it's fair to say that the whole problem is solved with this formula. And maybe it will surprise you if I tell you that the whole thing works exactly the same for matrices. This means every step we do here, we can also do for the n-dimensional system of ODEs. We only need the correct definitions. For example, we need to know how to deal with an inverse of a matrix and also with the product rule when matrices are involved. So maybe let's start with this product rule in the case that the matrix multiplication is involved. So let's simply say that we have two matrix functions m of t and n of t. And then we can form the matrix product if the dimensions fit together. And now the assumption we want to put in here is that the components of each matrix give us ordinary differentiable functions. So you already see we just have to deal with real valued functions anyway. So you could say everything happens in each component separately anyway. So for example, here in the top left corner, we would have m1j of t times nj1 of t. And then the matrix product tells us that we have to sum up these components over j. And then I don't have to write down more components because everything looks very similar to that. So this means we just use the derivative in the component, and there we can use our ordinary product rule. Or to say it more precisely, we first use the linearity of the derivative to pull out the sum, and then we have the product rule inside. Therefore, we have the whole sum and then inside a sum with two terms. And then the first one has the derivative on m and the other one on n. And that's already it, because now you see we can do that in every component, and then we can split up the two matrices. Hence what we get is the derivative of the first matrix function, which means the derivative in each component, times the second matrix function plus the other way around. So in other words, this nice matrix product rule follows immediately from our ordinary product rule. And in fact, we can immediately apply it to a matrix function which is invertible. And then what we should get is the differentiation rule for the inverse. So let's assume for every t we have an invertible matrix m of t, which means we can multiply with the inverse. And then obviously what we get here is the identity matrix for every t. In other words, the derivative of this product is definitely equal to 0. But on the other hand, we can also use our nice product rule to get a formula out. So this means what we get here is a sum where the first term is just m dot times n inverse, and the second term is m times the derivative of the inverse. And to make this really clear, we write d dt of m of t to the power minus 1. And now you should see, by bringing everything else to the left-hand side, we get a calculation rule for this derivative. And here you can remember this as a general rule for matrix functions. And it's simply given by minus, and then we have this term here. But we also have to multiply with the inverse of m from the left-hand side. So you see, it looks really similar to the ordinary differentiation rule we have for the inverse, but here we have the inverse matrix on the right and on the left-hand side. And with that we have all the properties we need for the matrices, and we can go back to our n-dimensional system of ODEs. So we finally will generalize our method of integrating factors. And then as in the one-dimensional case, the first thing we have to do is to look at the homogeneous part. And there we could say that we already have a fundamental matrix solution which we call u of t. And please recall, this means that every column is a solution of the homogeneous system, and the columns together form the whole solution space. And this means instead of the single solutions, we can just calculate with the whole matrix u of t. So we can just look at the derivative of the function u of t, which means we have the derivative in each column. And since each column is a solution of the homogeneous system, we just have a of t times alpha j of t in the column. And therefore we can also write it as a matrix product a of t times u of t. In other words, a fundamental matrix solution just satisfies the homogeneous system as a matrix. And now, as in the one-dimensional case, we can choose a really particular solution, so this one we call principal matrix solution. And this one is also given with respect to an initial value problem, so we say it's the principal matrix solution at t0. And the common name we have for that is just a capital pi. And then this pi of t is just defined as u of t times u of t0 inverse. So please keep in mind the inverse exists because we have a fundamental matrix solution. And therefore our pi is also a fundamental matrix solution, but fixed with an initial value problem. So what we get is that it solves the ODE as before, and it has the initial value given as the identity matrix. Hence, each column of pi here is fixed by the unique solution of the initial value problem. And exactly this justifies to speak of the principal matrix solution at t0. And now you might already guess that this pi of t should be our integrating factor in the method of finding the solution of our system. However, it's not quite correct, because as before, the inverse of this pi of t should be the integrating factor. Therefore, it definitely helps to know the derivative of this inverse. And now by the rule before, we already know we have a minus sign and two inverses, and the derivative of pi of t in the middle. So this is nothing new, but at this point you should see that we can substitute the derivative of pi. We can just write a of t times pi of t, and then we see this pi of t will cancel with the right inverse here. So we actually have a nice short formula here where a of t is involved. So finally, with all of that, we are ready to start the method as before. Therefore, in the first step, we just bring the homogeneous part to the left-hand side, and then we multiply with our integrating factor. However, since we have matrices where the order of the multiplication matters, I should emphasize that we multiply from the left-hand side. So we have pi of t inverse multiplied on both sides. And the result is as before. On the left-hand side, we find a sum which we want to rewrite as a product rule. And on the other hand, there's not much to do on the right-hand side. Okay, but now you should immediately see that the product rule on the left definitely works. This is simply because we already know that this term here with the minus sign is exactly the derivative of the inverse of pi. Which simply means that our integrating factor works and we just have to integrate on both sides. And then as before, we get the upper limit with x of t and the lower limit with x of t0. And moreover, we can use that we don't need to write pi of t0 because it's given by the identity matrix. And similarly, here on the right hand side, we cannot do much because we can just write the formula for the general integration. But obviously for our theory this is enough, because now we have our solution of the initial value problem. And as promised, it looks exactly the same as in the one-dimensional case, just with matrices involved. So in short, the scalar function p from before is now our matrix function pi. And this is quite nice because it means it does not matter in which dimension we have our initial value problem. So finally, we have a solution formula that covers all linear ODEs. In particular, this also holds in the important case that our homogeneous system is autonomous. And in that case, you already know that our principal matrix solution is just given by the matrix exponential. So also there, this formula helps you to find a particular solution of the inhomogeneous system. So maybe it's really helpful to look at some examples, but this I would say we do in the next videos. So let's meet there again and have a nice day. Bye bye.